Hey students, Mr. Danahauer here. Today we are going to get into our geosphere unit and start discussing the layers of the Earth. So what's underneath us where we're standing right now. And so we'll get into that. To get ready for this lesson, you should have your note guide that has a pie-shaped section of the interior of the Earth, a cross section, and divided into two sides, which we'll talk about here in just a second. So first of all, when we talk about the layers of the Earth, there are a lot of different ways to define these. So you might go, okay, well, what are the characteristics we're using to decide when one layer ends and the next layer begins as we go down into the Earth, right? And you can see from all these pictures, there's different ways to organize or categorize, I guess I should say, these layers. So we have crust, mantle, upper and lower, outer core, inner core, or just this one here, inner core, outer core, mantle, and crust. And then these have a few more details on them. They include a lithosphere. And so I want to be really clear when we talk about the layers, it's really important to distinguish what layers are we talking about? What are we using to define the different layers? As you can see in our note guide, we have two sides to the note guide. All right. On one side, we're going to be discussing the chemical properties and defining the different layers, which there are three of them, based on their chemical composition. Okay. And then we're going to shift to the physical properties, meaning what state of matter is this? Is it solid? Is it liquid? We don't have any gaseous layers in the interior of the Earth, which we can talk about. But what's the physical properties of that particular layer? So we'll go through each one, but it'll always be important. For example, if I ask you the question, what's the first chemical layer? You should think, okay, I'm talking about the chemical composition, not the physical composition. So real quick, you should pause the video and jot down these two definitions just real briefly so that you understand the difference between the two different criteria that we're using to define these different layers. Okay, so let's start with this is just a good overview. Okay, so you can see on this side, we have three chemical layers, the very thin crust here, and then the very thick mantle and the core. And you can already see what the composition is like for each of these, but the reason why we define these as three distinct layers chemically is because they're made up of different chemical compounds or elements, as it may be. And then on the physical side, you can see a quick guide here. We have 5 physical layers. So we go from the lithosphere, which is rigid, to the asthenosphere, which is more movable, and so on. So again, we'll define both of these and talk about each one. Okay, so one thing that's really important that as we go deeper in the Earth, it gets warmer. So I want to put some context around that because it's going to be important more for our physical layers. But I want to remind you that that's important, and then we'll come back to it. So let's start with the crust. Our first layer is the crust, and we're on the chemical side, the side of your notes that's divided into 3 sections, all right? And you'll see on the top there, it's divided into oceanic and continental. So geologists, seismologists, all the people who study this stuff, they either call crust oceanic or continental. And it's kind of obvious why that is. Oceanic crust is usually covered with ocean. And the reason for that is it's pretty thin, which we'll get to in a minute. And continental crust is thicker, and so it's usually considered to be a continent. So let's jot these down under these different types of crust. Remember, we're focusing on the chemical composition. What are these things made of? So first, oceanic rocks are typically made up of lots of ionic compounds that have iron and magnesium. So we have very high percentages of iron compounds and magnesium compounds. And as we discussed in our last few lessons, that's why we talked about different ionic compounds, names and formulas. Okay, these rocks are called mafic rocks. Mafic. And they're usually darker in color, which is more of a physical property, but I thought I'd put that here. And the reason we use this term mafic is it stands for ferromagnesium compounds. So ferro refers to iron. And if you look at the periodic table, iron is named, symbol is Fe for ferrous. That's the Latin term for iron. So magnesium is Mg, and so when we put those together, we get mafic for magnesium and iron rocks. Okay. Also, it's really important in oceanic crust. We don't have much silica. Silica is a silicone and oxygen compound, and we have a lot of silicate compounds in our crust, in our mantle. That is important to know, but the amount of silica has a big impact on how the crust can melt. And we'll talk more about that in a little bit. So the continental crust is chemically a little bit different. It's usually made up of rocks that are higher in feldspars and aluminum compounds, and they have a lot of silica and oxygen. So again, we have a lot of silica rocks. Just as we noted in the oceanic, there's less silica, but there's more in continental crust. Okay, and these are considered felsic. Felsic are lighter colored rocks, and that, I think I'm correct on this, but you can fact check me. Felsic stands for feldspar and silica, which are very common compounds or feldspar minerals that we find in continental types of crust. And these are typically lighter in color, pinks and whites, those kinds of colors. So continental crust has a high silica content. The reason that matters is when crust dives down in, which we'll talk about the tectonic plates in a few minutes, but if crust subducts or goes down towards the center, it can often melt, and then that molten rock can come up and form volcanoes. And the temperature at which it melts depends on how much silica it has in it. And it also dictates how viscous or thick the lava or magma is. So if we ever see a volcano from molten oceanic crust, it's usually flowy, that and pejojo. Those are different terms we use for lava flows. And that's the kind of lava you might see in Hawaii. It's just flowing like a river. If we ever have a volcano that comes from continental crust, like Mount St. Helens, it's very thick and it doesn't flow very well. So often when it's trying to come up and come out of the volcano, it clogs everything up and pressure builds up, and we can get really big explosions, just like we saw with Mount St. Helens. If you don't know what Mount St. Helens is, look it up. It's way before your time. I was a little kid when that happened. So that's an old reference, but famous volcanic eruption in the United States. Okay, sorry, let's keep going. So that's our crust. Our first layer it is very thin. The next layer down, which is somewhere, roughly 100 kilometers down to about 3,000 kilometers. So this is a very thick layer. And it is also made up of a lot of silicate materials made of silicon and oxygen. And there's a lot of magnesium and iron. So a lot more of these mafic type rocks in the mantle. And we have a few examples here of silicates. So one thing I will say is, we saw some similarities between the crust and the mantle in terms of chemical composition, lots of silica and oxygen compounds. And for our oceanic, lots of magnesium and iron or mafic rocks. And so there are some similarities between these, but there's a distinct difference when we enter the mantle. If we're going down from the crust to the mantle, we start to see a different percentage of these different compounds. And then our innermost or deepest, if you will, layer is the core. And again, in all of our pictures, right, those were divided into inner core and outer core. But when we talk about chemical composition, the entire core, both the inner and outer core, are made of the same substance. If I can get back here, okay, and that is iron and nickel. So these are elements. They are not compounds like the rest of the layers we were talking about previously. This is like iron metal and nickel metal, mostly is what we see in the core. Okay, this is mostly, if I remember right, it's mostly iron and some nickel. So now we might think about this, like why would we see the most dense substances found at the center? It's a good question to think about. Iron and nickel are much more dense, probably like 3 times as dense as those other compounds that we were just talking about, the mafic and felsic rocks, the silicates. Those rocks are probably in the like 3 grams per cubic centimeter, and iron is around 9 grams per cubic centimeter. So iron and nickel are quite a bit more dense. Why would they be found at the center? Now, we know that more dense objects sink and less dense objects float, right? But how can things sink or float when you're talking about solid rock? We have to think about when the Earth was forming. Remember, this is all theoretical. We can't go back and see it, but we have a lot of evidence to support that when the Earth was forming, it was very hot. In fact, the entire Earth was more of like a molten ball of rock instead of these solid layers that are mostly we see today. Okay, so when you have a more movable or fluid layers throughout, we get what's called differentiation. And that just means that more dense materials have the ability to sink towards the center, the gravitational center of Earth, and then those other layers differentiate based on their density. Okay, so I have to think about the history of the Earth to understand why things are the way they are today. It's also important to understand, why are we talking about all this? Let's just back up for a second. Why do we care about all these layers? Okay, because what happens up here on the top of Earth, on the surface or the crust, is highly determined by what goes on underneath us. Okay, so when we talk about the tectonic plates moving, when we talk about the magnetic field, which protects us from bad stuff that would kill us, all of these things are determined because the composition of our Earth is inside. Okay, let's go into the physical layers. So now we're shifting gears. We're not talking about the chemical composition on this side. Now we are talking about what physical property are these particular things in. So are they a solid? Are they liquid? Are they rigid? Are they movable? That's what we're looking at. So our first layer is called the lithosphere. And the lithosphere, I'm going to jump ahead real quick here and show you. The lithosphere is made up of, this is a good comparison. The lithosphere is made up of the chemical layers of the entire crust and then part of the upper mantle here. So we can see this is the chemical layers, the 3, and here's our 5 physical layers. Okay, so lithosphere is a little bit of all the crust and a little bit of mantle. And go back here. All right, so this is important to understand. It is solid and rigid. All right, you know that because you know all these rocks, they are solid. A lot of them, you can't break them, you can't deform them. They don't move in terms of like liquids or gases, that kind of thing. So this is a solid, rigid layer. That would be the best way to describe it. Hopefully you're writing all this down. If you do need to pause the video to write stuff down, just request that, and I'm sure that will be fine. Okay, let's move on to the next layer. Now this rigid, we need to also talk about physical properties of the crust, since the crust is in the lithosphere layer, and now we're talking about physical properties. Let's add a couple more things that are more physical properties of continental crust and oceanic crust. So number 1, I already mentioned this, but continental crust is typically thicker. Okay, if you, here in Colorado, it's very thick because we are a mile above sea level, right? And so this continental crust can be anywhere from 20 to 60 kilometers thick, roughly. These are just, averages and stuff like that. Whereas the oceanic crust is much thinner. So if we want to get through the entire crust and down into the mantle, it would be a lot easier to do that, like drill down through the oceanic crust because it's much thinner. Okay. And also, continental crust, because of its chemical composition, is less dense, and oceanic crust is more dense. Those mafic rocks those mafic rocks, I'm jumping all around here. The mafic rocks that are in the oceanic crust are a little bit more dense than the felsic rocks that we find in the continental crust. So that goes of another question. A lot of times, two different types of crusts will come together, and one is forced underneath the other. So which one would be more likely to go underneath if a continental crust meets up with an oceanic crust? And obviously, based on our matter lesson, the more dense oceanic crust is going to go under, or what we call subduct, underneath the continental crust. And we'll see that more in a few lessons when we talk about plate tectonics and all the features that we see here because of the plates moving around. Okay, good. And I mentioned plates, so you probably already know this, but all of the crust, or it's actually not the crust, it's the lithosphere. All of the lithosphere of Earth is broken into these giant plates. Right? You can see they're different color coded here. We have the giant Pacific plate, the North American, South American plate, and we have some smaller ones, the Nazca plate and the Caribbean plate. But all of these plates are rigid, but they are sitting on top of the asthenosphere, which is a movable layer. So let's go to that next. Okay. So this is pronounced asthenosphere. Okay. Asthenosphere. That's how we pronounce it. And it is the next layer down. And a lot of times this is described as a plastic layer. Why would we call it plastic? Plastic isn't a physical property. It's kind of a descriptor. If you think about plastic, plastic is bendable, it's movable. While it's solid, it's still movable. Okay, so this is a more flexible, more movable, or we might say more fluid layer. So if you think about that, we have a very solid, rigid lithosphere sitting on top of a movable plastic or slushy layer. So think about if I took a board and I put a bunch of marbles under it. So the board is rigid, representing the lithosphere. The marbles are movable, representing the asthenosphere. And I stood on top of that board. Now that board is able to move around. And that's what's going on with these plates, right? These rigid plates are moving. In part, they are able to move because they are sitting on top of a movable layer, the asthenosphere. Okay. So be clear, this is not liquid. Okay, we're not sitting on top of a liquid layer. It's just more movable. The reason for that, this is really important. I mentioned it before, but as we go deeper into the Earth, the temperature rises and it actually goes up quite a bit. We'll see in just a minute. But because when we know phase changes, right, matter becomes more fluid-like or flexible as it warms up. And if it gets warm enough, it can change to a liquid. So that'll be important in a minute too. Okay, our next layer is the mesosphere. Now, you rarely see any of these, if you Google images or look things up, oftentimes you don't see mesosphere. You see mantle, and upper mantle, lower mantle. And so we are going to use the term mesosphere because it is a scientific accepted term. Meso just means middle, and it is a solid layer, okay? And it's hot though. So that's really important. Again, as we get down, look at the temperature here. We're at like 15 to 3,000 degrees Celsius, okay? This is hotter than your oven gets by far. And so these rocks, while they are still solid, they are not molten yet, they do have the ability to move very slowly. Think about if I took a piece of plastic and I just warmed it up a little bit. If I push on it some, I can get it to move very slowly and change shape, okay? So again, this is a solid layer, but it does have the ability to move very slowly. And you can see in this animation right here, in the bottom, that we actually get what's called convection cells. And if you don't know what convection is, you should by now. But if you don't know what convection is, basically warm stuff rises and colder stuff sinks. Okay. In your basement right now, it's probably colder. Upstairs, it's warmer because warm air rises towards the top and cold air sinks. Same idea here with convection currents. The interior of the earth is hotter. It warms up the lower mantle here, and that creates these convection currents. As that warm mantle very slowly, we're talking like moving slower than your fingernails grow, guys, very slowly, okay? As these warm rock kind of slowly move up, they cool off and then they fall back down, and we get these giant convection cells. Convection is really important to understand for energy transfer, and we'll talk about it a lot in almost every unit, actually. We'll talk about it with the ocean and ocean currents. We'll talk about it in the atmosphere with winds, global winds. Convection is really important. Why does this matter? These convection cells, you can imagine if the rock here in the mesosphere or the mantle, the mesosphere is moving, then the stuff above it is moving too. So it's exerting a force. And when we look at our plates, why are those plates moving? In part because of the convection currents in the mantle. That would be a really good thing to write down. Okay. And you can see in this animation, right, we get some crust spreading right here because we have warmer magma pushing up and causing these plates to spread apart. So that's one example that doesn't fully describe it, but helps you maybe understand. So the movement, these convection cells in the mesosphere cause, the mantle really, because it's called mantle convection. That's causing our lithospheric plates to move around. Okay, so let's think real quick, go back. We have a rigid lithosphere sitting on top of a movable or plastic asthenosphere, and then we have our solid but very slow moving mesosphere. So our last two layers, chemically, it's the core made of iron and nickel, but they are different. The outer core and inner core are categorized differently because they're different phases of matter. So because it gets hotter as we go towards the center of the earth, we have a liquid outer core. It is hot enough to melt the iron and nickel. So it is molten and liquid out here. This is really important because the outer core is liquid. We get convection currents in the outer core as well, just like we did here in the mantle. And the convection currents in the outer core create the Earth's magnetic field. That is super important because that magnetic field that's created by the outer core, the liquid outer core, protects us from these solar winds. All right. These solar winds have they have high energy charged particles in them. When they hit the magnetosphere, it's called, that's our magnetic field. That magnetosphere deflects those winds and protects us from being cooked alive, basically. So if you ever want to, thank the earth or be grateful about the structure of the earth, one thing you should be really happy for is that we have a liquid outer core. Our studies on Mars show that Mars is smaller, right? So it's able to cool off a little more quickly. Earth is quite a bit bigger, so it's cooling off more slowly. And so Mars, we think, used to have a liquid outer core, just like Earth, but we are pretty sure it no longer has a liquid in it. It's cool enough that it's become solid. What that means is there is no magnetic field on Mars because there's no liquid core to generate it. And that means that if you ever go to Mars, when you go to Mars, you're going to need to be protected from those solar winds or they will quickly cook you and fry electronics and all of other kinds of things. So there's a lot of problems that occur because of the lack of a magnetic field on Mars. Okay. And then we have our inner core. Now this is kind of weird, right? It gets hotter. It's the hottest in the inner core. Real quick, why is it hot? Okay, there's two theories, and they might both be true. There's a lot of science going on to study this. It's pretty hard to study things that are 6,000 kilometers underneath you. Number one, it's really hot. And number two, there's an extreme amount of pressure. So you could never travel to the center of the earth without cooking or being crushed to death by the pressure. So some problems with even going to the interior of the earth. There's two theories about why it's hot in the interior of the earth. Number one, we have a lot of radioactive elements. And remember, we learned in our matter unit that radioactive decay gives off energy, right? All nuclear reactions give off energy. We have a lot of uranium and thorium and potassium that are radioactive or unstable. And as they go through radioactive decay, they give off thermal energy. And so that's one theory about why the interior of the Earth is generating heat. And the second is that as I mentioned, when Earth was formed, it was very hot. And as we also know, things are going to cool from the outside in, right? The outside of the Earth, the crust is exposed to, there's no insulation. And so it loses energy, thermal energy there. And then it continues from the outside in. And so some scientists say that the heat in the interior of the Earth is left over from when it formed and it's still cooling off. All right. Now, why is the inner core solid? It doesn't make sense. It's hotter. Remember that the outer core melted between 4 and 5,000. I'm just roughing the numbers. 4 and 5,000 degrees Celsius. If it's 6,000 degrees in the inner core, how is it possible for it to be a solid? It should be molten. And the answer is pressure. States of matter always depend on temperature and pressure. Okay, so because you have all of this other rock that's pushing down, even though it's very hot in the core, very, very hot, there's so much pressure that it stays a solid. There's not enough room, I guess, if you will, for those particles to have freedom of motion. They are stuck in a solid state. Remember, too, both the inner and outer core are made of iron and nickel, the metals, okay, but the inner core is solid for physical layers and the outer core is liquid. Okay, good. So just a quick recap. Here are our 3 chemical layers: the crust, the mantle, and the core. Here are our 5 physical layers: the rigid lithosphere, the plastic-y, slushy asthenosphere. I don't like to use slushy. We have that on the slide, but slushy to me, I think of like 7-Eleven slushies, and I think of cold and kind of like icy, and that's not a good description. It's more like warm plastic. So plastic is a good description for the asthenosphere. And then we have the rigid mesosphere that is movable, but just very slowly. We have our only liquid layer, the outer core, and then the solid inner core. All right. And just one more picture. We didn't talk about depth of all of these, but you can see it's roughly to the center of the Earth, roughly 6,300 kilometers. And you have to convert that to miles. Miles to kilometers ratio is about 6 miles to 10 kilometers. So you could do the math there and figure that out. Now, here's a good question. If we have only... I'm going to make some numbers up, so don't quote me on this. But we have only scratched the surface, literally, of the Earth. I think we have drilled down maybe 15 miles. My last check, I could be off on that. It might be like 20 or 25 now, but we really haven't gone down, dug down very deep. And I'm talking about small boreholes that we've punched into the Earth, right? So if you think about it, we have not even barely gotten into the mantle to study it. So how do we know all this stuff? How can I sit here and tell you all of this? And one of the answers is seismic waves, which we're going to talk about next time. So all this theory about the structure, the interior of the Earth, it is all theoretical because no one has ever seen it. But we will learn about how we study it and learn more about it and develop the theory in our next class on seismic waves. All right, that's it for this lesson on the layers of the Earth. You'll get into your dessert activity to practice physical layers. Have a great day and Sco Ridge.